bridge. All the piles were repaired during the 19th, and the last years they also repaired a lot of the edge beams that were suffering from reinforcement corrosion. A cost-benefit analysis between different repair works show that it would be it would be cost optimum to use cathodic protection. So we're in the middle of making cathodic protection on the remainder of the edge beams on this structure. Also on a steel harbor just south of Stockholm in Sweden. You can see some of the challenges that they have there. Probably the worst examples that I've taken pictures of. It's a quite large harbor structure where the first part is an area where we could gain knowledge on the system. We did in 2007. And now they have Monica, there's been some recession in the steel industry. So we are installing cathodic protection in this other end, and they want to do the rest here next year. We do zoning. This is the Nordic part of it. This is southern. We have to zone them so that they are operated individually, so it's not too vulnerable that it's not all of it that would go out. You can see the beams here with anodes on, and they are then cast in a floating mortar. The operation conditions are very difficult because the height here is very, very low. You have to make sort of more or less a military exercise to get underneath of these. And the rectifier cabinet also. So possible advantages. Well, it does both stop and prevent and arrest corrosion. You can keep it to a minimum the amount of chloride removed. If it's chloride-induced corrosion, you don't have to take all of what is chloride infected away, only the areas which is delaminated. That can be cost efficient in a longer time. And you need to, of course, know what systems you want to choose, and then you can have a long service life for those. Possible disadvantages. You will, for many systems, have an increased weight and altered appearance. You need to realize that you have a long operational maintenance ahead of you. Some systems, that could go for some of the conductive paintings. I only showed you a few examples on these. Some of them they have a limited current output and a limited service life. And potentially some different durabilities have been raised over the years. One is the hydrogen embrittlement, where we then have more strict functional requirements. Increased, as you could say, you migrate the chlorides, but so will the alkalis. So if you have reactive particles, there is a theoretical increased risk of ASR. You could choose, you would have to deal with that. I would say we've never seen any examples that this has been an actual problem. The currents are very small, so the migration of ions is presumably also very small. But something to consider if you have an ASR in your structure. Acidification at the anode. We've seen on a few drilled-in anodes high acid developing around some of them, but that's where they've had too high anode current density compared to the supplier's recommendation. Also, you need to have specialists in this area included in your design and installation of it. And all supplies has to be included in the repair schedule. I mean, normally when we have contractors doing repair works, they will just start in one end and then go on. Now they need to have input at different stages where the CP contractor needs to come into place. A few examples on CP on steel structures. Rouet sulfur expansion. You have your structure here with all the dolphins and piles underneath. You need to design what is the climate you're facing. This should not be milliamps, it should be amps. You have a design life, and then you have to. This is actually a long service life for sacrificial anodes. Normally it would be 10 or 15, 20 years max. But this is a client. You know what you have to select the type of anode, how you mount them. And you can do manual readings with a portable reference editor. So we do a design, and then we place the anodes on the steel structure itself. Another example I'm not sure whether this is the right English word, but it's a structure like this. What would you call that?
Is it a warning tape or?
Yeah, it's a marking. Well,
Like a station.
okay. Okay, then I can just as well guess myself. I don't know what, but yeah. Again, designing and you have to think the divers that needs to go in there. If you cannot mount them on site, they should not be too heavy. There could be an as-built situation where the coating was not as you anticipated in your design, so you need to update your design. Another container terminal with a very high salinity. A design where we estimate our best estimate on the resistivity of the water in the dive, but we didn't have any factual data on that one. How they are mounted. I'll just get on to. And then our guy in Kogi, we sent him off with a salinity meter, and we could then, it was at lower salinity, we did not need so many anodes for that, so we could update design based on actual measurements. So that's just saying that it's important to verify your design parameters. We've done windmill foundations, designing sacrificial anodes. It's a big project that we have out at the moment. That's been the project where the owner says that sacrificial anode, and we have to document that the polarization at seabed level throughout the service life is fulfilled. If you go to all standards and calculations and norms you normally do, that you can calculate the amount of steel, the amount of sacrificial anodes that you need to fulfill that requirement, but you cannot document that it's fulfilled for two reasons. This is the structure as such. You have it here as a drawing, and we have two racks here. The designers did not want anodes. You have to think that it goes deeper down here, so you have the racks with anodes. And so they wanted the anode placed locally here. If you place anodes close to one another, there will be a mutual interference between them. So they will not give out so much current as if they were placed further apart. That's one thing. The other thing is if you go down to the seabed level, or if you move further away from the anodes, you'll not be able to polarize the steel to the same extent. We've never seen any documentation that other structures have made monitoring where you've actually verified this. But the owner will now go and look for different examples and do actual measurements on other installations to see whether it's okay. This modeling is a 3D modeling. It's a cathodic protection design tool for both sacrificial anodes and impressed current anodes that we use for this purpose. Also a sheet pile system, upgrading a system. It's a pier in a harbor. Oh, that was a bit too fast. So you have the steel pile out here, and it will be replaced. So it's a new system that needs impressed current system, as per the owner requirement. What we did here is that we actually used some of the existing sheet piles for the cathodic protection. That existing sheet pile will disappear quite fast when we use it as an impressed current anode, but we can calculate that it can fulfill the requirement. When you have impressed current, you always need to look at the earthing system, if there's current drainage to the structures, if there's risk of stray currents, also to neighboring structures, yeah?
We had a strange thing happen here in the bay. We had a sheet pile of breakwater made out of sheet piles, interlocking sheet piles. It's no longer there, it's been replaced. It was made in England, Frottingham section, and it was there for a couple of years, and then we noticed all the interlocks started to disappear.
Yeah.
Have you ever seen that happen?
Yeah, we had a replacement of sheet piles along one of our motorway, and we saw some corrosion at the lock system. That's also to do with that was underwater.
Underwater.
Yeah, that's also to do with some sort of crevice corrosion. So you have areas where you locally have a very low oxygen concentration, so you can have more active corrosion in that area. Well, concluding, cathodic protection is an efficient way to both prevent / stop corrosion on reinforcement, and for many, in particular marine structures, but also structures which is de-iced, is a cost optimum solution. It should always be compared to other repair methods. One possible advantage is that you could have cases where removal of concrete is minimized. And if you look at the indirect cost in a repair work, that might be worth your while, so you don't interrupt your traffic for too long.